in chapter 8. One is treating water so we can drink it. That's what this subject is. The next one is treating water, sewage water. And then the last one is treating water that's salt water. Okay, because as we talked about how much water's on the earth, that's wonderful, but most of it's salt water. So what does that look like? So this is just a typical treatment facility. Again, this is kind of where sort of like where Billy worked before. Is that right?
Community service.
Yeah. Okay. Did community service there, and let's take a look at the words you need to fill in. So the word is screens right here. My little pointer. So we get the water from the groundwater or from surface water, like this is showing you lake. You pump it through screens, and your book will tell you, you take out the twigs and things like that. We're going to talk more, or we did talk actually on Wednesday about the different agents you might add to it to get flocculation, to get it to flocculate. Flocculating agents is the word here, flocculating agents, it's hard to say. Paddles. Here we have a settling tank after the flocculator, settling tank. And then charcoal. Charcoal, if you see the word charcoal, you're talking about a bunch of carbon. Carbon's great for taking out odors and impurities. Okay. And then we pump it on through. We can, I'm going to show you here in a minute options for dechlorinating, but chlorination is a good way to kill bacteria. And then this is a little controversial, the whole idea of adding fluorine, fluoridation. So that's kind of, a typical, and I went out online and tried to kind of find some there are definitely variations of this. So let's see what this video does for us. Okay, but it's interesting. This has nothing to do with chemistry, but don't you wonder, like how vulnerable maybe we are if somebody just wants to put something bad in there? I watch too much movies.
Oh yeah.
They test it all the time, but what if
one drop of something can contaminate the entire.
Yeah, and what if they put something in? They're familiar with what's tested, and they put something in there that's not tested. I know, right? Okay. So alternatives to chlorination. So they made their own chlorine on site. There's ultraviolet light is one option. It's expensive, and ozone is the other. Ozone, of course, is O3, and it's a good disinfectant for ultraviolet light. I think what I read in your textbook is even if they use UV light, there's still like a little topping off with chlorine treatment. So maybe they didn't care that you were mopping with chlorine products because they're like, oh, we need a little chlorine anyway. Fluoridation, your textbook would say that actually there's a little bit of controversy. Do we really need to add that chemical? And I think the way it goes, your textbook talked about people who don't have access to, honestly, a dentist, quite frankly. Fluoridation can go a long way to keeping them healthy. So, all right. So that was the potable water, the water we drink. This is the other one. I gotta share this with you. So, did you guys hear? And I heard it on my talk radio this morning about there's a study out there, the whole flushing the toilet thing. So we all know that, and I don't do it like I should, but at home you should close the toilet lid before you flush the toilet. Duh, right? And the thing about flushing the toilet is it takes a little bit of, it like aerosolizes it. Basically takes some water and kind of spreads it out in the spray. So then the thing is they studied public bathrooms. They studied public bathrooms, and they have actually seen the whole fecal spray thing going on. So it's like fecal matter is aerosolized and it ends up, yes. I'm sorry. Makes me, I know, but what are you going to do? You have to go bathroom. So maybe that's good where they have automatic flushers. So basically you stand up and you leave and it flushes. And maybe that's why some people don't flush. Oh my gosh, those sorts of things have been mind since I heard that. Anyway, that's the deal.
I've not seen the water will spray on the toilet seat. It happens a lot in my high school. So I never use the bathroom guys.
Yeah, and you know, there is something to be said for timing, you know, and you can try to find alternatives where you feel comfortable. But sometimes you just don't have those alternatives. Sorry. Right, sure. You know, there are ways. But these are actually a couple of different versions of treatment plants, and they have some similarities. I can't remember if I found it. You have the primary treatment, secondary treatment, and tertiary treatment. And your textbook, and I didn't bring it in as one of the questions we would discuss, but basically said if you could, tertiary means it's as clean as it's going to be, and effluent means it's leaving. So if you could take from a waste treatment plant and put it right into a municipal water plant, you know, there's something to be said for that.
They do that in California.
You do that in California?
Yeah, it's all one system in California.
There's something disgusting I'd like to share. At the hunting camp I worked at, is we're in mountains and whatever, you dig a pit for everyone. And
can you hear what she's saying?
that's where you go to the bathroom, and in the winter it's really cold, so the poop will just like
accumulate.
it'll just make it like a tower, and so that's how I remember the difference between stalagmite and stalactite. Stalagmite might touch your butt.
Oh, goodness.
Yeah.
All right.
That's gross.
Might peck your butt.
I just said,
It's a temperature thing, right?
yeah, like somebody, I never had to do it, but eventually somebody has to like go down with a shovel and knock it so it doesn't keep.
Building up.
I had a coworker who was in Boy Scouts, and he said at Boy Scout camp they were there for like a week, and they had like a trench that went to the bathroom in, and if you didn't want to go to the bathroom in the trench, you had to walk like 5 miles to the bathroom.
To a normal bathroom?
Yeah.
I don't know if you know that.
5 miles? I don't know.
I don't know.
I wouldn't be there because they're probably spiders, so, but anyway.
Yeah, he said there's big spiders.
Oh, all right.
Yeah.
I don't think I have a video to show you. One of the tests that if you're working at a treatment plant like this that you look for in the effluent is the BOD. It's biological oxygen demand. And you might be like, well, heck, you want your water for little organisms to grow in the water. But if you read it a few times, you think the reason little organisms can flourish in your water is because they have nutrients there. Lots of nutrients means that you have not cleaned your water. Does that make sense? Too many nutrients, and little critters will flourish. And actually, that's, so you want a low BOD, that's the word there, a low BOD. It's just and when I worked at the Iowa, I told you guys for years, I worked at the Iowa Army Ammunition Plant there in Middletown, Iowa. And I worked in their chem lab and in their metrology lab. But in their chem lab, they do these tests, the biological oxygen demand, BOD. So a low BOD means you have clean water. A high BOD means that actually you have little critters that are using the oxygen in your water. And the reason they're there flourishing is because they have nutrients. Okay. Another thing, kind of, I don't know if it's related to it, but my daughter has switched her shampoo to a shampoo that doesn't have sulfates in it. And actually, there's something to be said for, you know, we talked about kind of clean chemistry. The things that and I'm not willing to switch yet, but I'll think about it. You know, what we put down our drain has to go through this system. And kind of like we're talking about in California, it's going to end up on our drinking water. Sulfates and nitrates going down our drain or somehow entering our water system are hard. They're hard things to get rid of.
I think, is it in wine there's sulfite or something?
Oh, I think sulfite.
That's like bad for you in some way too, right?
I think so.
Sulfate was bad for you.
Yeah, that's what old lady said, yeah. She said, yeah, and that's probably, but there's a secondary reason to try to look at detergents without sulfates in it. I tried with shampoo, it was like, oh, no, but you know, sometimes shampoo can't do about 5 days. Anyway, so, and that kind of, and I don't think I included it, but it's just kind of in general, the part of trying to help our environment is trying not to damage our environment. So like using less plastics, you know, maybe looking at what we're using for cleaning materials. All right. So the last thing is we have a lot of salt water here on Earth. So how can we turn that salt water into fresh water? I don't know if you've kind of got the whole sense of it, but if you drink salt water, you're generally going to die if it's kind of what you're doing. Okay. So there's a couple of ways to get salt water clean. One of them is distillation, and it looks like this, distillation. And there's a good chance. One of the labs I still want to do, there's so many labs I want to do, so little time, but would involve distillation. I think we talked about it. Remember we talked about if you take crude oil and you get the fractions from crude oil, that's kind of what distillation does a little bit. So distillation is you heat it up, and then your water's gonna go up, and your kind of sediment, your sodium chloride is not gonna evaporate. So basically up here then, you need, and this is a thermometer. Oh, sorry, is there words here? Yeah. So salt water is right here. Thermometer is this thing right here. And then you need to go ahead and cool that vapor down to make it liquefy. So this is kind of a fun little thing. This is a condenser. Yep. You can kind of see that dark blue. That's like, that dark blue is the jacket of water outside of the fluid that's going to fall down. So you have a jacket of water cooling down your gas. And the way we do our condensers, we have cooling water in and cooling the bottom, and then let gravity kind of do its thing, but it's sealed here. It's like a sealed, like I said, kind of a jacket. And water out there. And then, of course, your stuff drips over here. And then what you end up with over here is distilled water. So that's one of two ways. And I got this from your textbook, and I'm not sure I read in your textbook, that this plant probably uses the other way, not distillation. So the other way is osmosis, or specifically reverse osmosis. But if you've done biology, which some of you have done, you're kind of familiar with this idea of osmosis. Osmosis is just something going from where it's moving to where it's less concentrated from where it is more concentrated. Moving to where it's less concentrated to where it is more concentrated. Move from where it's more concentrated to where it's less concentrated. It's been so long, oh my gosh, I took biology 10 billion years ago. But if that's my cell, and we have, say we have high NaCl, of course that's sodium chloride, then this membrane, we talked about like pH membranes being selective for some things. If it's selective for sodium chloride and it's low here, it's going to go from the high to the low. It's going to cross that membrane. Okay, that's osmosis. Reverse osmosis, and I've got a new take on reverse osmosis. Reverse osmosis does the opposite. It basically says, it takes somebody, uses pressure, that's the word up there, uses pressure, I'm going to show you a little video, and it uses it to take something from that's higher concentration to a region that's lower concentration. So reverse osmosis goes against the grain. Basically, it's low here, and that wouldn't be my cell because that's not how it works, but it would take NaCl, and which is what we're trying to get rid of in desalination, and go from low to high. And that's not a natural thing to do. This is natural, this is not natural. The way you get this to do it is by pressure. To me, reverse osmosis is just like, what's a good example? If you want to squeeze, if you're just squeezing it through a filter of sorts. A filter that will allow, in this case, sodium chloride to go through. So here's the video. I was what? Oh. Well, it should warn me. Okay. So you can kind of see the pressure, or this is your source of your seawater. We pressurize this. This is the membrane, and it is then basically pushing it through this membrane, which is selected for just water. And so water's coming out here, and we're taking the fresh water. And then this is our dirty saltwater. So that's probably what's happening in that fancy plant we looked at. All right. Okay, whew, finally. So let's take a look for a few slides at Part 8. Or excuse me, you know what I mean. Chapter 10, actually. Credit for being here. So you see what we got here. Now, anybody in here, who in here likes potato chips? All right, cool. Mashed potatoes? You don't like anything. Basically stimulates our heart. You know, makes our heart go faster, which actually, if you have heart issues, they say chocolate is one of those things that, you know, moderation.
Is that why chocolate's like a Valentine's Day thing?
Right, it is a Valentine's Day thing.
I've never thought of that.
I didn't know it was a heart stimulant.
It makes us feel happy.
I don't know. I
It
like
makes us
chocolate,
feel
so-
happy. Yeah, that was the word. Makes us feel happy. It stimulates our heart, and actually, there's a chemical, you know, and the reason our bodies can work is biochemistry, basically. So we have a lot of interactions between chemicals and our bodies. A neurotransmitter. So basically, chocolate, it says, is the precursor for our bodies making serotonin. Now, I've heard of serotonin, you probably have before, the happy molecule. So it can use, see, tryptophan, this guy right here. I wanted to explain a little bit this, like these structures we're seeing. Let's see if I can find an easier one. These are short for, maybe I talked about this before, but this actually is trying to show you the single and double bonds, right? You see the double bond oxygen, single bond nitrogen, hydrogen, and it's not showing it, but there's a single bond between this nitrogen and the hydrogen. Okay, now at the vertices, I think that's the word I want, at the corners are carbon atoms. So I'm going to put a little carbon atom there next to the CO2, next to the carbon. That's a nitrogen, that's a nitrogen. There's a carbon here. Okay, there's a carbon here at this corner, a carbon here at this corner. So unless they say, for instance, here it said NH, N is part of the ring. If it doesn't say it's a carbon, it's just shorthand if it doesn't say it's carbon. So over here, then on the ring, this 5-sided ring over here on the right, it looks like I could put a carbon here, right? And I already had a carbon there. We have a lot of ringed structures in biochemicals, so I kind of put a carbon there. Okay. The other thing about these structures is a lot of times they leave off miscellaneous hydrogens. So one of the things about carbon is it reaches out 4 times. Okay. So actually this carbon here, let's pick on this guy who's in the 5-membered ring over here on the right. That carbon is double bond nitrogen, single bond nitrogen. Well, hey, so that's 1, 2, 3, and it likes to reach out 4 times. So honestly, even though it's not showing, a person could look at this, and I'm going to put a bond here, and I put the hydrogen atom. So that's my -H. So that's the other shorthand notation we kind of use with these ring structures. Okay, so just to kind of show you. To interpret this one over here, the tryptophan, again, well, I'll start with this right here. This is wonderful. This actually is a benzene ring. So just like I did over here, I'm going to put a carbon, 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 carbon. I'm going to end up with 6 carbons around that circle. Carbon, 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 carbon. And if you count up bonds and all that, you're going to see that actually each of these carbons, at least the outside ones, have to be attached to a hydrogen. Again, just shorthand. We don't draw in those hydrogens. There's an H there, an H there, an H there, an H there. See how that kind of works? So that's what the little lines mean in this swim drawing. Okay, very good. Chocolate makes us feel happy. Okay, so chocolate also has anandamide, which is another neurotransmitter that targets something kind of like marijuana. But I don't know how to spell marijuana. M-A-R-I-J. Mary Jane. M-A-R.
Mary Jane.
J.
Let's put Mary Jane.
What? It's like
Cannabis.
Oh, cannabis. Yeah, cannabis.
Cannabis.
Cannabis, yeah. THC. Flavonols, it's this guy over here, again, a bunch of carbon, hydrogen, some oxygen. They're found in, they're great antioxidants. And antioxidants in general are good for our heart.
So chocolate's just good.
Chocolate is good.
Well, it's like dark chocolate.
Ah, that's true. That's what your textbook would say. Dark chocolate's the best.
I know, it tastes good.
Dark chocolate's what? And actually, get your plates out. And someone, can you help give everybody one of those? Can you help give everybody one of these? What chocolate? What's that?
So what chocolate?
Right? And you guys, I won't do anything. You guys have to open these up and give everybody one of these. Or two. And I don't know where Natalie is, so go ahead and put something on her plate. I think she just didn't want the whole,
Yeah.
she just want the whole apple potato thing.
And we have a sauce one too.